Hello, my name is Volodymyr Metachuk. I am your host for this video, and I'm going to present you a high-level explanation on the concepts and the ideas that you can find in the article entitled "On the Theoretical Limits of Gradient Descent for Simple Recurrent Neural Networks with Finite Precision." So the main result of this article is the exhibition of regions in the parameter space for simple recurrent neural networks that cannot be reached by gradient descent in finite precision. The summary of this video is the following. We're going to start the discussion with finite precision and more precisely with the rounding error phenomenon. Then we'll proceed on defining simple recurrent neural networks and the beta saturation hypothesis. We'll discuss the benefits of the beta saturation hypothesis, and then we'll discuss the strategy that we adopted to derive our result. So, as I mentioned, this is going to be a very high-level explanation. We are not going to discuss any specifics or the constants that you can find in the article. So let's move on. Finite precision arithmetics are very similar to the arithmetics that we use to perform with an abacus, the main difference being that computers are way more efficient. Floating point arithmetics allow computers to deal with very various magnitudes, very large, small, and everything in between on a limited hardware, with the main drawback being that computers have a hard time dealing with large and small magnitudes simultaneously. To illustrate this drawback, let's consider having two float numbers, x and y, and suppose that x is a large float number. One can observe x plus y equals x even though y is not equal to 0, and this occurs when y is relatively small to x. So this phenomenon is called the rounding error, and please keep it in mind till the end of the video. So let's move on to defining simple recurrent neural networks. Simple recurrent neural networks, or shall we call them SRNs, are a class of deep learning models designed for sequence for processing sequences. So in the article, in this presentation, we consider the classification task, but in the end of the article, we discuss possible extensions to other tasks. So let's consider having a sequence of length t of vectors that we'll call xt over here, and an initial hidden state vector h0. The execution of a SRN r theta on the sequence xt is defined by the set composed of the sequence of all hidden state vectors produced by r theta and the output vector yt that we'll use for the classification. So this set is defined recursively following this rule over here, that we decompose into two for readability. So we have zk, which is a linear hidden vector, that shall we call them linear hidden vector, and it's a linear function of the previous hidden state vector and the current input vector. And if we need to produce the hidden state vector hk, one has to apply a nonlinear activation function on zk. So the nonlinear activation function that we consider in the article is the sigmoidal logistic function, whose output is in the range 0, 1. Therefore, every hidden state vector will be in the hypercube 0, 1 of dimension d, d being the dimension of the hidden state vector. Finally, if we want to produce the output vector, one has to apply a composition of a linear function on the last hidden state vector, ht, and an activation function. So here we have a visual representation of the execution of r theta on the sequence xt. Just to draw your attention to theta, theta is the vector composed of all parameters, and it is a handy notation for what will follow. Another remark that I would like to make is that we have, with no further hypothesis or assumption, we have no control over what will happen with the sequence of the hidden state vectors. We know that they will be in the hypercube 0, 1 dimension d, but we have We have no idea what will happen with the dynamics. Therefore, we introduced the beta saturation hypothesis. So we'll say that R theta in SRN is beta saturated if one can find a positive real number, beta, such that for all input sequences, every linear hidden vector that will be produced by the beta saturated SRN R theta will have this particularity of being in absolute value, coordinate-wise, greater than beta. So it is easier to understand with an illustration. So let's assume we have a two-dimensional hidden state vector. Every linear hidden vector that will be produced by the beta saturated SRN theta will land in one of these regions, one of these purple regions, and always avoid this middle cross. So if we apply the activation, we obtain that every hidden state vector will land in one of these small squares near the vertex, near one of the vertices of the square 0, 1, and more generally the hypercube 0, 1 of dimension d. So one of the first benefits that we can observe straight away of this hypothesis is that we have more control, more predictability about what will happen with the dynamics of the hidden state vectors. Other benefits of the beta saturation is that beta saturated neurons are stable to noise. So what is meant by to illustrate this effect, we plotted some graphs of the sigmoidal function where we evaluated on x plus alpha times some noise, and alpha being the volume, the amplitude parameter of the noise. And what we can observe here is that if we are far enough away from the origin, if we go beyond like something like beyond 6 here, the noise has almost no effect on the activation function. So a noisy neuron will in a beta saturated regime will have almost the same behavior as the not noisy counterpart. And this resilience to noise is directly linked to the derivative of the activation function, which is plotted right here, and we can see that it's almost 0 if we go far away from the origin. So how did we use the beta saturation? So in the article we show that beta saturated RNN, simple recurrent neural network, are resilient to noise in the fact that you can inject noise at every iteration in the execution of the SRN, and basically if the noise is small enough, it will accumulate but never explode, and we can control this. And so what it means is that if we have a beta saturated SRN R theta for a convenient beta, we can perform a small shift in the parameter space. We can add a small vector epsilon to theta and still obtain a beta saturated SRN with a slightly different beta, but it will have a very similar behavior to the original beta saturated SRN theta. So this is very handy because we can build around the parameter. We can build the parameter vector theta. We can build a small neighborhood of other simple recurrent neural networks that will have a very similar behavior to the SRN theta. The other benefit is on the gradient part, obviously. So from the backpropagation through time algorithm, we derived a expression of the gradient that allowed us to, in the beta saturated hypothesis regime, to upper bound coordinate wise the gradient by this expression right here, which takes the form of a convergent series if the beta is large enough. So obviously in the article it's all about controlling every quantity and so on, but here the high level idea is that we can bound the gradient by a convergent geometric series, and so if beta is large enough, this quantity here will be very small, and basically in finite precision, what will happen is that it will have no more effect on the parameters if we perform the gradient descent algorithm. So this is very interesting, but it's important to show that there exists at least beta saturated SRNs, and we exploited the finite precision in another way also, is that if we have a beta larger than 89, oh well, there is a typo. Sorry about that. Then the function, the activation function sigma, if we evaluate it on plus or minus beta, then it will have a very binary output, 0 or 1. And using this phenomenon, we were able to adapt an algorithm from the 60s that allowed us to construct for a given finite state machine. We can construct a saturated simple recurrent neural network that will simulate this machine. This allowed us to produce a set of parameters that will induce a beta saturated SRN. So on this slide, we show a graph that exhibits, resumes our whole strategy. So the build parameters that will induce beta saturated a beta saturated SRN and a SRN that will simulate the DFA is represented here with this yellow dot, and we'll call it theta target. So in the usual machine learning practice, we initialize parameters near the origin or here, and that we call theta 0, and then we apply the gradient descent algorithm, hoping that it will bring us to the set of parameters that will solve the problem. So we displayed here in this dashed line the best path that the gradient descent algorithm can take. And what we show is that theoretically, even if we follow this best path, the gradient descent algorithm will fail. It will produce the gradient will be rounded to 0 somewhere in this region. It will fail before reaching the target parameters. In practice, what we showed is that this failure will occur way before. The last remark that I would like to say is that we show also that we can have a set of parameters that will produce a failing gradient, even though the parameters will not solve at all the task. We will have a non-zero loss. We can even have a very high loss, even though the gradient is very near to 0. So thank you for your attention, and goodbye.